Hey guys, this is equation of a straight line question number 2. Identify the rate of change and initial value in the word problem below, and then write the rule for the linear relation. So a couple of things before we start. The words rate of change, we know that that's code for the A. So in y equals ax plus b, rate of change is A. Initial value, we know that is code for the B. And we know the rule is y equals ax plus b. So we're looking for information from the word problem that follows that's going to indicate a rate of change or an initial or starting value. So let's have a quick look at it. It says an Olympic-sized swimming pool, when filled, contains 2,500,000 liters of water. And then a crack develops at the bottom of the pool, must be at the big O, causing it to lose 70 liters of water every 2 minutes. Now, this little business with how much it's losing every 2 minutes is a little bit awkward, and we'll take a look at how to deal with that. But what I want you to notice is two things. One, this is what's causing it to change, right? To lose is another way of saying to change. So this is what's driving the change in the amount of water in the pool, and that relates to the rate of change. So this 70 liters every 2 minutes has something to do with the rate of change. In other words, it's going to have something to do with our A. And I'll point out to you that because the pool is losing water, that rate of change isn't adding. In other words, we're not going to end up with 2,750,000 liters of water or 3 million liters of water. We're going to progressively have less and less of that 2,500,000 liters of water, which means that change is a negative change, right? We're shrinking in terms of the amount of water that's in the pool. So just something to think about there. But I want to start with the amount of water that's actually in the pool. The pool, when the problem is starting off, before that crack opens up, has 2,500,000 liters. This is what's known as the initial value, because that's a starting value. Right? To start is 2,500,000 liters of water. That's going to be our B. So in y equals ax plus b, we already know our B. Our B is at 2,500,000 liters. That brings us to the issue of the rate of change. Now, typically, we know over here, typically speaking, we don't kind of measure how things change every 2 minutes. We tend to think about how much it changes every minute. So if we analyze the rate of change really quickly, they've kind of hidden it on us in this problem. What we know is that we're losing 70 liters per 2 minutes. And when we're doing rates of change, we don't want them measured in 2 minutes or 2 hours or how much it changes every 2 years. We want to know per year or per minute or per second or per single unit measurement of time. And so 70 liters per 2 minutes, we know that works out to, if we go 70 divided by 2, we know that comes to 35 liters per minute. And we know we're losing that 35 liters per minute, as I said, because of the notion of a loss. In other words, shrinking or the value going down. And so now we're ready to plug in our A and our B into our formula. It's pretty straightforward at this point. We're going to write y. So the amount of water that is in the pool at any given time will depend on how much time goes by. And we know that we're losing 35 liters for every minute that goes by, but that we started out with 2,500,000 liters. Just quickly remembering that the amount of water in the pool depends on how much time has passed. The amount of water in the pool depends upon, so that's the dependent, how much time has passed. And as I manipulate the amount of time that passes, 1 minute, 2 minutes, 3 minutes, 100 minutes, that will affect how much water remains in the pool. And you can see that I'm going to subtract from that 2,500,000, 35 liters for every minute that goes by. And that's a real basic word problem with a rate of change and an initial value.